All right, everyone. Welcome to recitation 2. Today we'll be covering the following topics. So I'm going to talk a little bit more about bandits, cover some stuff from lecture, and anything that could possibly help for homework 1. And then we're going to talk about Markov decision processes. And at the end, there's going to be time for questions for homework 1 or even anything about the course content so far. All right, so from last week, here's a sort of quick summary of the 4 algorithms that you will be asked to implement for your homework and how they're different. So remember again, epsilon greedy is the simplest one. We always exploit, but with a small probability, we choose a random action. And this is the simplest thing, but the downside is that over time, you're still exploring actions that don't possibly give you the highest value. Then we have optimistic initialization that works by setting the initial values higher than the true rewards. And as we average the rewards over time, they'll start to go down. And that's how exploration and exploitation is balanced. We have UCB that sets an upper confidence bound on the true value of the action. And this confidence bound over time starts to reduce because we are more certain of what the true reward of a certain action is. And that's how exploration and exploitation is balanced. And then lastly, we have Boltzmann exploration, which was not covered in lecture, but there's a part about it in the book and also in your homework. Very simple. It just uses a probability distribution that's similar to a softmax function. And with a certain probability, it will choose a certain action. Okay. So when it comes to implementing these algorithms, there's a pretty simple framework that you can use. And this is like some pseudocode for that. So you need some sort of data structure to record the Q values and the counts for each action. And then you repeat the following loop, not forever, but a certain amount of, depending on the number of time steps, that many times. And for epsilon greedy, you choose the action by either picking the greedy one with probability 1 minus epsilon or a random one with probability epsilon. That action part would be changed depending on the other algorithm that you're using. So for Boltzmann, you'd use the following formula, which is on the top right. And for UCB, you'd use the one on the bottom right. They all have a different hyperparameter. For Boltzmann, it's the temperature, symbolized by tau. For UCB, it's the confidence value C. And for optimistic initialization, you're always picking the greedy action, but the initial Q values that you put, they wouldn't be 0. They would be something that is higher than the true reward. So that's how all these algorithms could be implemented. And after that, you'd update your counts based on what action you've chosen. And then you also update your Q value for that action based on the true reward that you get from picking that action. Does anyone have any questions about how you would implement this? Yeah?
Yeah, in the Boltzmann is sample from this probability distribution. That's it.
Okay. Anyone else have a question? Okay. Then another thing to note about the homework is what we are asking you to plot. So we ask you to plot some graphs in the later part of the assignment, which you can do through matplotlib. Most of the code is written out for you, but if you need to, you can read the documentations for this library. And it's important to know the difference between the true reward and the expected reward. So the expected reward is what happens when we multiply the probability of an action by the reward it gives. And this is only relevant to do in some of the algorithms because some of them use a probability distribution and some of them just pick greedily. So it's up to you to figure out which ones have a different expected reward and true reward. So the Q value, remember, is an estimation we make of the value we get from choosing a specific bandit, and it's updated using the formula you see at the bottom. So we update Q by adding onto the old value the actual reward minus our prior estimate of what it was, multiplied by the number of times we've picked an action. So keep in mind that the R over there, the reward, is the true reward, okay? And what we ask you to plot in the homework is the expected reward. So if we look at the epsilon greedy algorithm, for example, most of the time we'll pick the greedy action, and when we do so, we get a specific reward, that would be R, but that is not what we are plotting. We would have to plot what the actual reward is multiplied by the probability of picking that action, and also the probability of not picking that action times the other rewards that we could have got. Yeah, so just keep that in mind when doing the homework, that they're two different things. Does anyone have any questions about that? Yeah.
The rewards are also probability distribution, right? So do we need to take expectation over that as well?
No, I can double check that answer, but I would not think so, because when you're comparing the performance of the different algorithms, you're still using the same true rewards. So it's still fair because they're, yeah. Are there any other questions? Okay. And then the last thing that we ask you to do is to consider what environments these algorithms could be effective in. Remember, in lecture, we talked about what the issues are when environments are non-stationary, which means the true rewards change over time. And can someone think about why certain algorithms might not be effective if the true rewards are changing?
Some algorithms, like they just use the one with the max reward so far. So if something originally has the highest max reward, and then doesn't change, and then the other values get higher max reward over time, then the algorithm is just going to really pick that one forever, and then not note that the other ones have higher max reward like later in the future. Exactly.
Yeah. So you're losing out on potentially really good actions because the true values are changing. We talked about a solution to this was to use recency weighted averages. So a priority is given to the more recent rewards, and you basically forget what the initial rewards are. And so it's important to think about that for your homework. Are any of these algorithms able to handle those environments effectively or not? Any questions about that?
And I'm just going to quickly go over the other major concept that we covered this week, which would have been Markov decision processes. And then at the end, I'll probably explain about how it's going to be relevant to your homework, and especially in the policy iteration and value iteration part of the homework. So just a quick overview of why we're using Markov decision processes as opposed to bandits. The main reason why we use Markov decision processes is that it allows you to convey the idea of states. If you recall from the bandit problems, one of the key characteristics of the bandit problem is that no matter what arm you choose, you're still going to be resulting in the same state, which means that you're still going to be presented with the same actions. And at least assumed in lecture, those actions will maintain their same reward functions and the reward distributions. But that isn't realistic to most reinforcement learning problems. Most reinforcement problems involve this idea that if you take an action, you're going to be in a new environment. Well, not a new environment, but a new state that has different values and rewards that are attributed to specific actions. So we need to also be able to consider this idea of state now. I also just want to quickly emphasize that this is a major simplification of most problems you will see that actually appear in the real world. MDPs often just serve as a quick introduction to the basic problems and the notation so that we can eventually jump to those more advanced problems in the real world. So just a quick terminology overview. There's some new things that we need to consider and some old things from the bandit problems. The first new thing is often known as a state space, which just represents the different possible states that your agent can be in as they go through the reinforcement learning problem. From the bandit problem, we also have the action space, which represents the different actions you can take at any given moment. The only key difference that I would remark on between this and the bandit problem is that the action space can also depend on the given state you're in. If you recall from the bandit problem, the action space stayed constant. You have your given amount of bandits that you can pull the arm of, and those don't change because the state doesn't change. But because the state changes now, the actions that are available to the agent might differ. Like for example, if you're up against a wall in a maze, you obviously can't run into the wall. So that's how the action space could adapt based on the state space. The other thing to consider is the transition functions. Basically, this entails how taking a specific action in a given state will transition you to the next state. We often represent this as a sort of probability distribution. This is to represent the stochasticity of taking actions that could potentially lead you to different states based on just factors in the environment. The function in a mathematical representation takes in a state which is going to represent the future state, the state that you're going to assume that you might land in, as well as your current state and the action you took in the current state, and spit out a probability, the probability that you will transition to the S prime, the future state, given that you took in action A in state S. And then the last thing that we want to consider is a reward function. The only difference between this one and the bandit problem is that we also need to consider this idea of state. So this is going to map from your state and an action and map to the reward that you would get for taking that action in state S. This next bullet point is just something to consider. I don't believe we covered it much, but there's always a conflicting notation you might see out there in this lecture, as opposed to more problems you might see in research papers as you read. Other ideas convey this idea of combining the reward with the transition function. So instead of just representing the probability of reaching state S prime, given your current state in action A, you can also represent the idea of getting to state S prime and getting reward R, given your state and your action. And then the other thing to consider maybe is that sometimes reward functions aren't based off the actions, they're more based off state transitions. In this case, your reward function would be based off your current state and the resulting state. So instead of S by A, you'll have S by S to a real value reward. And then the last bullet point I just wanted to quickly cover for this class is that we'll mostly be considering finite MDPs for this section of the class. This is to basically mean that we have a finite action space and finite state space, as you will probably see in the problem. Infinite state spaces and action spaces are often a difficult problem, and we just want to give you a quick understanding of this MDP, not to consider infinite possibilities. Are there any questions about MDPs in a general sense? All right. So I just wanted to give a quick example of what an MDP might look like. In this picture, you can see that the 4 different aspects that's been introduced. Okay. So in the big green dots, we see the different states. So those will represent our state space and the potential states that we can land in. We also look at the red dots, which represents the actions we can take in those given states. And then key features include the transition probabilities demarcated by the arrows. The black arrows, they represent the different probabilities of ending in a new state, given the old state as well as the action. So one I will point out is if we look at this line right here, we'll see that the probability of reaching state S sub 0, given that you started in state S2, and taking action A0 is 0.4. And then this also represents a key characteristic in most reinforcement learning problems, which is that you will notice that most of the transitions have a 0 reward, which is very common for most problems you will encounter. Like maze problems, you won't get a reward until you get to the end of the maze. So most of the lines have no associated reward, but some do. And in this case, we're noticing that the reward stems from a state to state transition, because it's focused on the part of taking the transitioning to a state instead of the actual action part. You'll see that transitioning from state S1 to S0 gives you a +5 reward in this case. Are there any questions about this example? All right. The other main concept I just wanted to quickly cover is what makes the Markov, includes the Markov part of the name, is this idea of the Markov property. This is the idea that the current state encapsulates all past information in the trajectory. The formal representation of the functions that we want to be, the transition functions, usually encapsulates this dependence on all past actions and trajectories, because that's the more thorough way to represent this transition functions, because we have obviously been through that trajectory and that's relevant to the current problem. But the Markov property basically allows us to encapsulate all that information and simplify that trajectory into one state representation. Now, this is important for when we're developing our state and how to represent that state, that we need to make sure that it conveys enough information to be able to represent all past trajectory. So this allows us to simplify this otherwise extremely long dependence on past trajectory into just what the current state is. And now that I've rambled long enough about what MDPs are in general, what can we do with this MDP structure? Obviously, the main goal is to learn a policy. And this policy is going to map from your state space to the action space. So what actions should you take in specific states? And we ultimately want to land on the policy that can maximize the discounted reward, which brings up the question of why we want to be discounting the reward. This is basically meant to deal with the idea of infinite trajectories. It's very simple to imagine, if we go back to the other side, that we could potentially end up in a situation where we're just looping through. In fact, this is one that you would just be looping through different states with no terminal state in sight. The idea of discounting it is so that we don't result in this situation where you have infinite reward, because that doesn't really give us a lot of information. It also incentivizes early action depending on what you set the discount factor at. This is branching off like the human idea of like inflation, where money and reward is more now than in the future. So we also want to do that with our discount factor. Are there any questions about this purpose of the MDP?
Over one, this is not relevant, right? So over one,
You will see this in the policy iteration and value iteration part. That part does cover MDPs.
policy iteration, value iteration part, we know the full dynamics. Where does discounting come into play? I mean, we can get to it.
Yeah. I believe that we'll cover a little bit later, but that might be part of your calculation of
Yeah, I was just confirming that for homework one, we don't really interact with the environment and it's all finite, and yeah, the episode length is also finite.
I believe there is a terminal state in homework one, which I think you might also need to, like, if you have a policy that doesn't take you to the terminal state, just maybe also factor it in.
Also, maybe to add on to that, even if you don't have infinite actions, a discount factor can still be used, because then you're still incentivized to find like the shortest path. Yeah, to find the thing.
And then in terms of learning the policy, there's two other relevant functions that we need to consider. The first is the value function that maps from states in the state space to their estimated value, which is based off the rewards as you've experienced, as well as projected other estimates of values in other states. And then we also want to consider the Q value, which basically maps from a state in action to the estimated value. This is just a more complex version of the value function. It just wants to consider that additional information of a specific action. So the important thing to note here is that if you have the Q values, you also have the optimal actions to take in a given state. Yeah, so this is how obviously the policy will operate. It will try to, you'll see it from the homework, that it tries to basically take an argmax of the Q values to see which action is the best in any given state. This brings up the exploration versus exploitation problem. I just wanted to quickly, given what we know about MDPs and our knowledge of the reward and transition functions, I wanted to ask if anyone had any opinion on whether or not we needed to explore in this environment or take explorative actions instead of just taking the optimal at all times. Yeah, this is sort of a nuanced question to look at, but I just wanted to quickly bring it up. Because as you probably have experienced in the bandit problems, we've had a need to explore. We can't just always take the optimal action because there's a possibility that the actions we haven't explored are better than the optimal one we're currently taking. But the thing to remember for MDPs, as we presented, is that we have access to important pieces of information, which are the reward function and the transition function. Because we have access to the reward functions, we don't really need to explore in this case because we already know about what the given rewards are. And the problem we're facing here is just how to find the proper policy to maximize those rewards. We don't need to explore because we sort of in our head, because we're given the reward function, know what the reward is for taking, say, action A5 in state S2. We know that, so there's no need to start exploring randomly. And then the last thing I just wanted to quickly cover is how it's relevant to you in homework 1. In homework 1, we will be asking you to implement policy iteration and value iteration. As presented in class, policy iteration and value iteration are almost the same things for identifying the best policy for a given MDP. The key difference being that in policy iteration, you will want to converge to an estimated value function for your given policy before you improve your policy by argmaxing over the different Q values versus value iteration, where you only just do one quick sweep over the given states and estimate the values before you do the policy improvement step. And then the other thing to consider that we present in homework 1 is this idea of synchronous versus asynchronous updates. In synchronous, you basically maintain two different copies of your value function. This is the idea that when you're updating the value function, as you go through the different state space, you want to maintain and only use from the past value function. Because as you guys can imagine, as you're updating the value function, you're changing the values of the different states. And sometimes, we'll discuss the pros, but the synchronous tries to maintain the stability by only using the ones from the past value functions as you update it, versus asynchronous, which as you update the value function, the value for a given state, if you need that value for the calculation of the value of a different state, you can use that updated value instead. And that should be basically cover most of the stuff you need to know for MDPs. Yeah?
I think the synchronous and asynchronous sound counterintuitive because I would think that synchronous would keep updating the values and would be in sync with the new values.
Yeah.
The definition switched.
Test switches. Oh, I swapped the definitions.
Maybe.
Wait, let me just make sure. Is this switched? Okay. Okay, wait, that might be swapped. Wait, do you see? I think I was looking.
I think it might be swapped, but
Okay.
we can.
Yeah. Shoot, I might have messed up the notation.
Yeah, I think the way you said it, yeah, the definitions I think seem to be swapped. Like synchronous, yeah, would be at the same time.
I think I'm not saying it's wrong. I'm saying it just seems counterintuitive. So
I
Yeah,
understand
I don't
what
see.
you mean. We'll confirm on Piazza, but I think it might be switched. Yeah.
Yeah, I'll confirm, but I just want to clarify this is the main difference, right? The one where you update from all the past value functions as opposed to a version where you update from the values that you're updating. Yeah, I'll just make sure to follow up this on Piazza.
Sure, that'll be great. Thank you.
Are there any more questions about MDPs in general? If not, I think we can open up the floor to, this is basically the end of our presented part of the recitation. And the rest of the recitation will mostly just be focused on if you guys have any questions about homework 1.
Or about the course.
Or about course content.
Yeah.
I think, how do you suggest like working in a team on homework 1? Like how do you divide tasks? Like since you need to implement algorithms.
Well, I think it could be like up to you, but I know one way people do it is like part 1 and part 2 are usually split. But I think it's important, even if you do work on different parts, that both people understand.
Yeah, so our doubt was like the exams are still individual. Obviously, we all want to learn all the content. So, weren't really sure how to go about it.
Yeah, I guess with bandits, for example, like there's four algorithms, and each person could do 2, or even like think about things simultaneously. That could also help.
Are the homeworks going to get longer?
Yeah, this is easier than the following homeworks.
Yeah, I'll add on that I recommend I'll be opposed to splitting up. I would recommend that each person works on one part so that their knowledge about the bandit problem isn't lacking because they only did the MDP part of the problem, the homework. So I would recommend that all group members work on, like, say, part 1 and all members work on part 2. I know that I use like GitHub, like version control to help coordinate between different members. So that might be something you might want to look into.
So that's totally doable for this homework because it's, I mean, I don't think it's that not realistic, but as we get harder, we might not have a choice to do everything. Yeah, we might need to split up.
Yeah.
Yeah, one thing I would say is like usually like if you work on something like as a group, like it takes you way less time than like working on things individually. Because if you just find like all the bugs like immediately because you have 3 different people that are looking at the same code at the same time. It's like actually like I found it's like sometimes like significantly quicker to like work on something as a group. Like if you have 3 things, like having a group do each of those 3 things is like, significantly faster than having each person try to like do like one thing. Because then like there's bugs that it's hard for them to find. But like if the whole group like does all 3 things, it can be like very quick. Because if you like don't like actually like do like 1 or 2 passes when everyone looking at it, like there's like no like you like finish it. So it actually can be like quicker like in a group. And also it's good for like understanding of things.
Yeah. I was like, it's up to your group to decide. I would just recommend like what he said, where it's like working together, trying to find that common time in your schedule to work together is very beneficial. Are there any more questions about homework 1? I know we released it recently, so. There's no. I guess if there aren't any. Oh yeah, what's up?
For the submissions, how much work should we show in LaTeX, or is this what do it for like? I've never submitted a homework on LaTeX. well, what should that look
Yeah.
from the greater feedback?
From the latex, so I think our expectation is that you'll be uploading you'll like take screenshots of your plots, and then those will be the elements that go onto latex. And then there will be a code submission aspect of it. You just upload your files, and we just want to make sure that you had the right idea when implementing the function.
And I don't know if this homework requires it, but if we ever do like written on paper math, would you like that to be typed into LaTeX as an equation, or can we like upload a scan into the LaTeX, like a figure, which is just like a scan of our math, do it by hand, for showing our work?
I think you can take a picture and put it in the LaTeX as long as it's legible. That's just the most important thing. I don't think we're gonna penalize on like how nice it looks, but like we should be able to read your answer. And then I guess for the homework, there's like the actual like questions list, and then there's a LaTeX file where you're meant to put your answers in, and I think it kind of explains like what each part is looking for. So
if there are any more questions about homework 1, that we can just wrap up the recitation there. Thank you guys for coming. If you have any more questions you want to ask us personally, feel free to come up to us. Other than that, have a nice day.